Today we have Shu Shao. He is from Texas A&M University. So now motion capture is a fascinating piece of technology, and Microsoft has done a lot of work over the past decade designing things like the Kinect, for instance, which has brought this technology to our living rooms, literally, right? And this has enabled lots of applications. Today, Shu is going to talk about how to make this even more practical and take it outside of our living rooms and bring it to our lives even closer. And he's going to talk specifically about human pose tracking using this motion capture technology, and he's going to focus on using inertial sensors. Shu is a robotics researcher. He works on search and rescue robotics at Texas A&M University. His advisor is Robin Murphy. She's a very well-known figure in the field of robotics. And I'll hand the floor over to Shu now. He's gonna continue talking. Thanks. Welcome.
Okay, thank you, Shuaib. So, hello everybody. Good morning. Welcome to my talk. So today I'm going to talk about articulated human pose tracking with inertial sensors. So my name is Shu. So I'm from Texas A&M University. I have been doing this internship in Microsoft Research Audio and Acoustic Research Group for 3 months. So this is like a summary of what I've been doing in the past 3 months with the group and with my mentor, Shuaib. So to begin with my motivation of the project, so I want to explain what motion capture actually is. So motion capture is a process of recording and digitizing movements of an object or a person. So it has been widely used in filmmaking industry, in video games, in virtual reality, in augmented reality, and also in healthcare. It also finds applications in other fields as well. So the existing MOCAP system, what we have now off the market, so most of the MOCAP system falls into 3 categories. So the optical system, the non-optical system, and the hybrid systems. So for the first category, the optical system, so people usually use markers, either passive or active, which is attached to the subject's body, to the body segment. And we use cameras to track the motion of these markers in the 3D space. Then we recover the motion of those markers and correlate the motion with the corresponding body parts. Thus, we can recover the motion of the subject. There's also markerless motion capture systems, such as the Kinect we have in Microsoft. It's using depth sensing without any markers. There's also works on like only using visual cameras to recover the motion. So the second big category is non-optical systems. So the non-optical system means we are not using cameras at all. So basically, every sensor is integrated onto the human body, so we don't need like an external sensor. So the most widely used non-optical system is inertial-based, which use IMUs, inertial measurement unit. It measures the inertia of the sensing unit and then reproduce the motion of the sensor frame. We also have a mechanical system to do motion capture, such as exoskeleton. And magnet systems is only useful in a very smaller scale, like for sensors in the blood vessel, in the human organs, in a very small scale. So the third category combines the first 2 together. So using both inertia and optical to achieve a better tracking result. So here I will play a video of a very famous existing optical MOCAP system. So as you can see here, it's in an indoor lab with multiple very costly infrared sensors. The setup is quite elaborate, and it requires people to well position the sensor first, and then precisely calibrate every single sensor, and then attach multiple markers onto the human body. Then motion capture happens afterward. So I will play the video here first. So the whole motion capture happens in this indoor like lab environment. It's well calibrated, and you can see all the markers, infrared markers on the body. So it takes a long time to put them onto the body and calibrate them. So this constrains the application of this kind of optical MOCAP technology in a very limited capture volume. So here is another example of the second category, like the non-optical. So it's used inertial sensing. And this is the, so using inertia, that means we have to deal with sensor drift, lot of noise from the IMUs. So, but you know, for this technology, in this particular company is doing pretty well. It can achieve a pretty precise, pretty good accuracy, but it's still not 100% accurate, not compared to the optical one. But it does not require like cameras. As you can see, the subject needs to attach multiple sensor modules onto the body and then calibrate them and put them in the correct position and do the actual motion capture afterwards. Let me play this video. So he is trying to beat the record, so it takes like 3 minutes to put on everything and start a MOCAP. So it's still wired to the computer, and then takes all the information from the different sensor modules and try to compute the motion and put that motion onto an avatar, as we'll see here. Yeah. So for the existing MOCAP systems, especially inertial MOCAP system, what are the problems? So usually those systems are limited into a very finite capture volume. So it's in a studio. You cannot bring that outside of the studio. And it needs very precise sensor calibration. You need to position the sensor at a good position, and then you need to calibrate it with respect to your body frame. So since we have already calibrated the sensor, we need the position of the sensor to be invariant along the whole motion process. So we use rigid sensing positioning, so it's with straps. So the problem with straps is not very comfortable and it's intrusive. You cannot have the straps on your body like 24/7 for a long time. So and the system is also not portable. So we cannot bring the system, wearing all the sensors and work anywhere in our daily life. So, but is there any way that we can solve all these problems in one single system? So imagine if we have a system, a MOCAP system with inertial sensors that is fully integrated directly into your garments, into your everyday clothing. So this system would be non-intrusive at all. So it's just naturally embedded into your clothing. And it's mobile. You can wear your clothes anywhere. So you can also bring the MOCAP anywhere. It's lightweight, just a couple sensors and a couple processors on the daily garment. And it enables long-term tracking. So you don't need to do motion capture for motion capture. You can just do your own stuff, and then the motion is automatically captured at the same time. So the most important thing for this technology we propose is it opens up lots of new applications in such as health monitoring, sports training, augmented reality or virtual reality. Lots of things we haven't even thought about before will be enabled by this technology. So this is the whole motivation for my internship. For the 3 months project here, I have been trying to accomplish this with the hardware, with the data set, and with the algorithm to deal with the issues, the intrinsic issues within this proposed technology. So the first step, for sure, we need to go beyond straps. So we don't want to strap everything onto your body. We want to integrate that into your daily garment. So in an initial study we did last year, so we find out if we didn't like rigidly fix the sensors onto your body parts using straps, the noise is pretty high. So basically, inertial sensing is already, we have to deal with a lot of noise already. And if we didn't rigidly mount the sensor onto the body with straps, the noise is even higher. So it's more difficult to recover the motion with a reasonable accuracy. So this is the outline of what I've been doing in these 3 months. So first of all, using the first month, I built the hardware. I set up a custom-built studio to collect the data for this project. So for the second month, I implement a kinematics algorithm as a baseline to do motion capture. It includes calibration, sensor fusion algorithm, and I also quantify the sensor movement, and also for joint angle estimation. So for the last part of the internship, I tried to use machine learning techniques to solve the noise, to solve the sensor movement problem using deep learning DNNs. So this is the outline of the talk. So basically, I will go over everything I have been doing in the 3 months, from hardware to data collection, kinematics, machine learning, and future work. So this is the snapshot of our actual hardware. So it's 7 pieces of clothing, 1 jacket, a pair of pants, 2 gloves, a hat, and a pair of shoes. So there's 38 IMUs and 8 infrared sensors embedded into the system. So this is outside of the system. So you can see it's just like everyday clothing. But when you look into the inside-out view here, you can see all the sensors are stitched or embedded into the system. So in order to keep up with the data rate, because we have so many sensors, we use lots of individual microprocessors. 3 CPUs for the jacket, 1 CPU for the pants, and 1 CPU each for other accessories. So this is the sensor layout. As we can see, the whole body is covered by a very dense body sensor network. So the circles represent IMUs, and the square represents infrared sensors. So the whole body is covered. So basically, we have a lot of redundancy for the sensors. So this is the hardware specs we use. So for the IMUs, it's a 9-channel IMUs, includes tri-axis accelerometer, tri-axis gyroscope, tri-axis magnetometer, and 1 single channel, an extra channel for the temperature. So for the infrared, we also have an ambient light sensor module integrated, but since the sampling rate is pretty low, we didn't include the ambient light, only the infrared proximity values. So for the CPU, we use an ESP8266. The CPU has its own Wi-Fi module, so it's self-contained. It has its own battery. It will just stream all the data through Wi-Fi to our host machine. This is the system diagram. So on the left-hand side, all the sensors are connected to 1 or 2 or even 3 layers of multiplexer because we have so many sensors altogether. And the mux will talk to all the individual CPUs. The CPUs pull the information or the data from its connected sensors and compose a UTB packets. So every single CPU is doing this and send all the packets through Wi-Fi. And the through Wi-Fi, the UTB messages will be received by a router. So the router sends it to our local host machine. A logger running on our machine will try to assemble all of the packets from different CPUs and timestamp it and save it into our local hard disk. So that is how the system works. It's self-contained. We don't have any wires for it as long as it's charged. So this is the studio setup we use for data collection. So for ground truth, that's very important for our research. We use our own Microsoft product, 2 Kinects, located on the 2 corners of the studio. And we fuse the 2 stream of point clouds together, and we use a third-party software to register them together and recover the subject's motion. We also have a flat screen TV in front of the studio, so the subject could face the screen, and the left-hand side of the screen is an actor performing the motion which is desired. And then the live video feed of the studio is fed to the right-hand side of the screen, and so the subject can know what he is actually doing, if he follows the actor right or not. So I will play a video here about the whole hardware and the data collection process. Oh, come on. Need to click on here.
The jacket contains 20 IMUs and 8 infrared sensors.
Each body segment is covered by at least 2 IMUs. Infrareds are placed between the torso and sleeves. All the wirings are covered by an extra slipped layer inside the jacket. Because of the sensor density, 3 separate CPUs are pulling the data and sending them with UDP packets. On the pants, there are 8 IMUs and 8 infrared sensors. IMUs cover the lower and upper leg while the infrared sensors face each other in the middle. One CPU with Wi-Fi module is located on the hip part of the pants, since it is the most stable position during motion. For each shoe, one CPU is connected with 2 IMUs and 1 infrared sensor. 2 IMUs locate at 2 sides of the shoe, and the infrared sensor is on top of the toes. An independent battery powers all electronics on one shoe. Same as shoes, gloves have their individual CPUs and batteries. There are only 2 IMUs on the hat, no infrared sensors. In the studio, all hardware is being charged at the charging station. The 2 connects locate at 2 corners of the studio to capture ground truth motion. The capture volume is marked by the blue box on the floor, while the T-shaped marker denotes where the subject should stand. In the front side of the studio, a wireless router receives all UDP packets. The subject faces a flat-screen TV, which shows the example motion the subject should follow and the live video feed from a video camera. On the other side is the second connect. The whiteboard is used to calibrate the 2 connects so that the 2 streams of point cloud data could be registered to the same global map. We are using IPySoft to calibrate and for ground truth collection. Ground truth collection is only based on depth sensing, so no markers are necessary to be mounted on the subject. Each subject is supposed to wear a pair of compression suits as a base layer before they put on the hardware. All subjects perform a T-pose at the beginning of all the motions. This is to calibrate the displacement between the IMUs and the body segments. All CPUs are pulling data through the multiplexers from the individual sensors, then compose and send UDP messages to the router. The subjects need to perform 5 different motions for multiple times. They are upper arm motion, lower arm motion, arm swing, boxing, and working. The subject can monitor his or her motion through the screen by comparing his or her motion in the live video feed with the actor whom he or she is supposed to follow. In the control center, the operator could monitor the subject's motion through a mirrored screen, start and stop the example trial for each motion. The UDP packets are collected by a Python logger and saved as text file on a computer through Wi-Fi connection to the router. The master IPySoft recorder is displayed next to the UDP data logger. This is the final structure of the dataset. The dataset is composed of the data and ground truth. Ground truth is in BVH format, provided by IPySoft Motion Capture Studio. The motion files are stripped from the BVH file. It contains the joint angle motion values only, not the skeletal hierarchical structure. Each data frame is composed of an absolute timestamp and 9 packets from all 9 CPUs. Each single UDP packet contains its relative timestamp and then the data from all IMUs and infrared sensors. IMU data is in the order of accelerometer, magnetometer, gyroscope, and temperature. The first 3 has 3 degrees of freedom, and the data is in XYZ order. Infrared sensor data contains the proximity value. So after we collect the data set, so this is the result of the whole data set. We have 5 different motions in the data set, and each motion is repeated for 2 to 6 times. 12 subjects in total and 215 trials. So the whole frame number is around 500,000. So the sampling rate is around 30 Hertz. So for the ground truth, we use the 2 connects and the third-party software to get the joint angle values. The ground truth is given as a BVH file, as I talked in the video. So it contains hierarchy part and motion part. So this part is not that much important because we don't care about position tracking. We only track the rotational and joint angles, and we use a predefined skeletal model. So this part is not important for us. So what we really care about is the motion part. So the motion part contains a big matrix, which each Each of the column represent the channels, like the joint angles, like my middle spine, my left arm, right arm, and each row is in each individual timestamp. So this is our ground truth. So after I finish with the hardware and data collection, I'm going to talk about the kinematic algorithm I developed in the internship. So in order to use the IMUs, the inertial sensors, we need to know the way to get the orientation from the data stream of the IMU. So IMUs are composed of a gyroscope, accelerometer, and a magnetometer. So how would so each of them has 3 channels information, X, Y, and Z. How would we fuse them together and get a real estimation of the orientation? So for the gyroscope, we have the angular rate. This is the quaternion representation of the angular rate, and use a quaternion product here, we can get the rate of change of the orientation. And we just use a simple integration over time to get the absolute orientation of the sensor. So this is the estimate from the gyroscope. And on the other side, we have accelerometer and the magnetometer. So these two things are trying to estimate the orientation based on a unified field, which is the gravity field for accelerometer and the magnet field for magnetometer. So, and the solution is not always unique. So we need to use a gradient descent optimization to get the estimation. So there is some math here, which I'm not gonna dig into deeply. So the take-home message is that we can estimate the quaternion of the orientation by a gradient descent by playing with this convergent term, which guarantees that we get the optimal solution. So from this slide, the take-home message is we have 2 estimations, one from gyroscope and one from the unified field from accelerometer and magnetometer. So the next step is to fuse them together. So simply, we can just use the weight to fuse them together. But the weight we assign here, the gamma t, needs to guarantee the convergence of the estimation. It needs to govern the fusion process to go the right direction. So there's also some math here. So we need to choose the optimal convergence rate by picking the proper value beta. The beta is defined as the divergence rate of the estimation from the gyroscope. So we can apply this term, and this is the final equation for the rate estimation. And again, we integrate it over time t. We get the estimation. So also the magnetometer has magnetic interferences in indoor environment. We need to compensate that by this term. So this is the whole block diagram to get the sensor fusion. This is an existing algorithm by Magic, so it's a pretty robust and pretty precise sensor fusion algorithm for IMUs with little computational overhead. So after we know how to define how to get the orientation from the IMUs, we also need to know how to represent a point in 3D space. So every single point in 3D space can be represented in different coordinate systems. So, for example, it can be represented in the coordinate system B2. It can also be represented in the coordinate system B1. So, but if we want to express the point from in B2 in the coordinate system B1, we need to apply a rotation or transformation matrix, which is defined here. It's a 3x3 matrix here. So it is correlated with the 3 Euler angles associated with the transformation of the 2 frames. So the Euler angles are defined as theta x, theta 1, theta z. So the correlation between the rotation matrix and the Euler angles could be defined by this matrix or the inverse of that. We can also recover Euler angles from the rotation matrix. So we are trying to estimate different frames attached to our body. So there are 12 frames or 12 rotational joints from middle spine all the way to right foot. These are the 12 joints we want to estimate using our algorithm. So then in the actual motion capture process, we need to define 3 separate coordinate systems. The first one is the global frame G, which is fixed to the Earth frame. The second is the body frame for each single body part, for the upper arm, for the lower arm, for the thigh, for the shin. We attach one body frame B. And for each sensor, we also have a frame sensor frame S. So as we can see here, this is the initial calibration process. For the calibration process, we ask the subject to perform a T-pose. And the purpose of that is we try to align the global frame with our body frame, G with B. The one here denotes sensor 1 or body part 1, like upper arm or lower arm. And then if we can align both of them, the transformation from B to S and G to S could be identical. So RS1 to B1 is equal to RS1 to G. These two are identical. That's the whole purpose of calibration. We know these two values are identical, and then we perform the actual motion. So in the motion, we denote the motion after frame the frame after motion with a prime. So the body frame after movement is B prime, and the sensor frame after movement is S prime. So we have two more frames here, S1 prime and B1 prime. Of course, the global frame doesn't move. It's fixed to the Earth. The Earth doesn't move. So it's still G here. So we have another two transformation is from the sensor frame 1 prime after movement to G, and the body frame 1 prime to sensor frame 1 prime. So these are all the coordinate systems and the rotations transformation we defined. So after the definition, we can go into the kinematics chain, go into the equation, and try to recover the joint angles. So back to the representation of a point in the 3D space. So if we have point P here in the 3D space, we can represent it in the global frame for sure. So which is P represented in G, PG. So we also write it here. So, and also we can represent the same point in our body frame after motion, B1 prime. So we denote this as PB1 prime. So in order to transform this representation from B1 prime to G frame, we can apply all this chain of rotation, and then we can get the proper representation in G, which is PB1 prime rotates from B1 prime to S1 prime and S1 prime to G, and then we get the representation in G. So by the same token, we can do that in a second set of sensor frames and body frame. So if it's in the second body frame B2 prime, we can apply the same transformation and put it into the G frame.
So what is B1 and B2 separate joints?
Yeah, they are separate. B1 and B2 are separate joints. So basically, they are connected joints. For example, upper arm and lower arm. So also like upper arm and my torso. So this is the body frame. So we can, since the left-hand side of the equation is the same, we can equate the right-hand side and rewrite the equation here. So we can still apply the rotation again on between the B1 prime frame and the B2 prime frame, which is we can transform P in B2 prime into B1 prime using this rotation matrix. And then we plug this equation into this. So PB1 prime will be represented as this, and we can cancel the PB2 prime on both sides of the equation. And then by some matrix multiplication inversion, we can put this term on the left-hand side and all the others on the right-hand side. So let's think about what is this term, RB2 prime to B1 prime. So basically, we want to express the second body part frame in the first body part frame after motion. This is exactly the motion we want to capture. If we can have this value, we know how the second body part is moved with respect to the first body part. This is the value we want to do motion capture. So we have this equation, but can we get all those values from our sensor? The answer is yes and no. So we can put some inversion here, and from this line, we have the sensor 1 prime to B1 prime. This is the displacement of the sensor frame after motion to the body frame after motion. This is something very hard to reconstruct using like free-mounted body sensors. That's why all the inertial-based technologies out there are using straps. So they want to make sure this is a constant. So S1 prime to B1 prime never changes. It's always the same value as calibration. So for the kinematics baseline here, I was just trying to make a very strong assumption that these are the same. So for the sensor frame with respect to body frame after motion is the same as calibration. For the sensor frame 2, it's also the same. So after make this assumption, everything in this equation is known. So as we can see here, so we assume through calibration, B1 is equal to G. So we can equate these two together, and we can equate these two together. B2 is also fixed to G. And these two are nothing but the output of the sensor fusion algorithm from the IMUs. So with that, we can compute the joint angles. So this is the result of the kinematics baseline. So the left-hand side is the overall joint angle error through all the 12 joints on the human body. So we can see the error is very large here. This is all the sensors on the jacket. So, but this is intuitive things when you move and you're wearing a loose jacket, this jacket moves with respect to your body a lot. So, but on the pants, even you work, it's less obvious. That's why you have this trend here. So jacket has correlated sensor movements, so which introduce significant error on upper body joints. On the other side, I also look into the dynamic response of the tracker. So as we can see, for the left elbow and left knee, the error increases, and also the deviation increases when I increase the motion frequency. If I move fast, the accuracy is bad.
So why is it decreased? Isn't it a 3D point, a 3D angle?
Yes. So for this, I plot all the angles for each joint. So each joint could be represented in 3 angles. I plot all of them, and this is the normalized all angles among 3 of them. So I can compute one value from the 3 angles. So this is only 1 dimensional, and this is 3-dimensional. Yes, the norm. Yes. So this is the error correlation matrix. We want to know how the errors along the whole body is correlated. So from this matrix, we can see if it's red, it means it's highly correlated. So what we can observe here is, so if the joint angle are estimated by sensors on one single piece of fabric, then the errors are very highly correlated. For example, on the jacket, all the joint angles error are highly correlated. Also on the pants, and also on the bridges between 2 pieces of fabric, such as from the jacket to the pants, from the pants to the shoes, or from the jacket to the hat. So these are also highly correlated, as you can see in this graph. So we also want to look into the performance in the time domain. So this is an example profile of the left shoulder for a particular subject. So the blue line is the ground truth we captured from our kinects, and the red line is our estimation from the kinematics algorithm. So there's lots of errors, as you can see in this graph, but each of errors could be explained, it could be elaborated. So for example, at the first stage of, at the calibration stage of our MOCAP, so we perform calibration. So we assume during calibration it's a T-pose. For this, we assume all the joint angles are 0, 0, 0. But it is not necessarily the case. Sometimes there's errors in there. Some subject may move the hand a little bit. It's not completely 0, 0, 0. That's what we call calibration error. So with the kinematics baseline, assume it to be 0, but the ground truths tell us there is a little bit offset here. That's the calibration error. And also after when the subject starts to move, so the body parts moves right away. So that is captured by the MOCAP system, the ground truths, the kinects. But the sensors on the garment may not directly follow the movement since it is loosely mounted. So if we have so it may move when the fabric stretches. So it moves with the fabric, not with your body segment. That's why we have a sensor movement latency here. And the third error source is from the sensor displacement. Since your sensor moves around your body part, it cannot give you a rough, a precise estimation of the movement. We can also see here, even if the ground truths go to the same, almost the same location, it has a different estimation from the kinematic algorithm, since the sensor has already moved. So it's very hard to get rid of these. Okay, so as we can see, the assumption is very, very strong here, the invariant sensor displacement. But how bad it actually is on the garment embedded sensors. So we try to quantify this using an analytical way. So remember, this is the same equation we have. we have this assumption, we equate this, we can drop the prime by this strong assumption, but using this equation, we can write it here. So it is also possible to put this part, the assumption part, on the left-hand side of the equation and put this on the right-hand side. So this is the joint angle estimation from the ground truth tracker. We can easily get those values and plug this into the equation. So the other two, these are the IMU sensor fusion output. So one problem here is this term. So what is this? This is the second sensor's displacement on the second body part. So basically, it's the counterpart of this, but it's the second one. So we cannot solve these two unknowns in one single equation. It's impossible. So here, we propose to fix an anchor point on a relatively stable sensor, aka on the head, or we can also fix on the left or right foot, but here we used our head. So if we fix this anchor point here, so the invariant displacement assumption is still valid at this point. So we get this value, we can plug this into this equation as the first equation through the whole kinematic chain. From the head, we can propagate this piece of information along the whole chain and get the displacement of all the sensors. So the result of the displacement analysis is this. So on each limb.
So go back to this slide. So if you pick an anchor point, something else, is that going to change anything, or is it going to?
Yes, it's gonna. If you pick the anchor point from here, it will change something because the error will accumulate along this direction of the chain. If you fix the anchor here, the error will be accumulated here. That's the problem. But the thing is, I will talk later about the machine learning algorithm to learn this amount of displacement. So that means we need it to be, so if we plug this information back into the equation, if we plug the ground truth, it will be 100% accurate. It's perfect. But if we try to fuse them together, there's error related with that. We will get back to that later. So this is the result. As we can see, so each graph is for each limb, like left arm, left leg, right leg, and torso. We can observe here is the displacement of the sensors is very drastic on the upper two limbs. It's pretty stable on the torso because the sensors are almost fixed on the torso. And on the legs, it's in between. That's what we find about the displacement. Okay, so now we are done with the kinematics. I'm going to the machine learning techniques we have applied to solve this particular problem. So, oh no. Okay, so we have implemented two approaches to use DNN on this particular problem. The first one is to learn the RSB, the displacement from the sensor to the body part. So we use the optical joint angle, which is the ground truth, to compute the ground truth sensor movement, RSB. And then we plug this RSB into the displacement equation and then get the joint angle. That's the first approach we tried. The second approach is an end-to-end joint angle estimation. So we feed in the network all the IMU data, and then we try to recover the full pulse of the human body. So we tried different sensors, single sensor estimation, which means one single sensor for one body segment. We also use sensor redundancy to test if redundancy can help us to reduce the error. And different sensor modalities means we also include the value from the infrared.
So this is the most stupid way you can solve the problem. Just throw the data into the neural network.
Yes, for the preliminary result, yes, it is. But we will see the result in a few slides. So the learning RSB approach, it's the same equation. We generate all the ground truths using the ground truths from the optical tracker. So we plug the fixed angle point into the equation, we propagate this, we calculate this, and then we propagate it to here, and then we calculate this. All the way, we can get all the displacement for all the sensors in terms of a rotational matrix. And then we transform it back to Euler angles. And the Euler angles is the ground truth for our DNN output. So we try to feed in the IMU information to the network. We train the network and get the displacement. We use the displacement plugged back into the kinematic equation. We get the joint angle estimation. That's the first approach. So the second approach is end-to-end. We feed in the sensor values. We try to estimate the joint angle values. The joint angle ground truth is just directly given by our optical tracker. So in order to prevent overfitting, we also did experiment on the training loss and validation loss. As you can see from this profile, the validation follows, the validation loss kind of follows the training loss, so which means our network is not largely overfit. So we also try to tune the network parameter to get the best result. We experimented with number of layers, number of neurons, and window size, and also different sensor modalities. Single sensor, multiple sensors, and plus infrareds. So the best performance architecture for now we achieved is using multiple IMUs, 4 dense layers network, 128 neurons per layer, and we use 7 frames per context window. Means we feeding the 7 frames altogether into the network, and we get the estimation of 1 single frame of the joint angles. So this is the overall result of the 3 different approaches. This graph you have already seen in the kinematics. This is the learning RSB approach, and this is the end-to-end DNN approach. So you can see the arrow drops along these 3 graphs. So the DNN has the best result, while the learning RSB is in the middle. So we also want to look into the time domain. The 4 curves.
So what is the average error like?
Yeah.
What is the number for all of these?
For this, the average is 15 degrees. For this is around 12. This is less than 8. That's the average for throughout the whole data set, the 500,000 frames. Yes. Yeah. So we also want to look into the time domain. These 2 curves represent the estimation from the 4 different trackers. Blue is still ground truth. Red is still the baseline, so they are way off because of all the uncertainties we talked about. And the learning RSB, the sensor displacement learner, gave us the gray line, which kind of represent the blue profile here.
Why is that a standard track?
So this is because of we have to feed the ground truth embed in information from the sensor fusion, and the sensor fusion algorithm is very noisy. We also have the noise embedded into the ground truth, which means our prediction from the network is noisy. So we have to apply a very aggressive filter on this. This is the filtering result. Since through calibration it's all 0, but it's filtered out, so this is why there's a huge slope here. So this is the so as we can see for the green line, the DN output, it is the best output through among all the other 2. So the green line represent the blue ground truth line pretty well. And we can see the result in the video in a minute. Same thing for the dynamic response. So the green and the magenta line is the old line you have already seen. But using our best architecture, our best approach, we can achieve these 2 lines, the red and blue lines. So it's not that sensitive to the change of frequency, and the overall error drops significantly.
So Shisu, you in the DNN solution use it not only the IMUs but also the infrared sensors, right?
Yes, we experimented with that, but the final, the best performance we achieved is without infrared. With
Just
multiple
IMUs?
sensors. Just IMUs, yes.
This is
No
impressive.
infrared. Yeah.
He showed three sets of experiments. The first one is just the single IMUs. Second set is redundant IMUs, meaning more than 1 IMU or 1 body segment. The third one is with infrared.
Yeah, different modalities. Yes. So here you will see the result, the tracking result in a video.
The first motion is upper arm movement. Starting from the key pose, the subjects need to use the shoulder joints to move the upper arm and reach 4 extreme positions. Since both the baseline and DNN tracker assume 0 translation and rotation of the hip, we manually fix the hip of the ground truth tracker so that they could be better aligned. This is why the legs are moving a little bit in a not quite natural manner in the ground truth, since it is the hip of the subject which is actually translating and rotating. The second motion is lower arm movement. The subjects need to use the elbow joints to bend the lower arm to reach 3 extreme positions. This is the motion with the best capture result, since the least amount of body parts participate in the motion, which makes most of the sensors stay in an invariant relative position to the body part. In terms of motion frequency, the first two motions are more static than dynamic. The third motion is arm swing. The subjects swing both of the arms forward and backward. The whole motion of the T-pose is completely dynamic, and most of the upper body is in a very fast motion. This leads to a drastic movement of the sensors away from their initial positions on the body segments. And as a whole piece of fabric, the garment will correlate the movements of different sensors. The trackers cannot precisely capture the accurate joint angles. The fourth motion is boxing. The subjects extend and retract the arms in front of their body. Similar to arm swing, it is very dynamic. However, since the range of motion is relatively limited compared to arm swing, the tracking result is slightly better. The punching of left and right fist is still recovered by the tracker and is distinguishable from the DNN output. The last motion is working. The subjects need to perform a normal work. All four limbs are in motion and most of the joint angles are rotating. In the baseline, the legs moves ahead of arms, which contradicts the video. This is due to the UDP packets don't arrive in order, and in this case, the different CPUs on the jacket and pants are not well synchronized. However, we can see the DNN tracker can track all four limbs with a reasonable accuracy.
Pretty good.
Okay, so this is the conclusions of my talk. So what I've been doing in this project, so I developed a new system for MOCAP with sensor placement uncertainty. So we integrate the sensors onto fabric. So it's wireless, it's self-contained, it has high bandwidth, and it's mobile. And then we produce a new time-synchronized MOCAP dataset. We synchronize the data stream from 38 IMUs and 8 RF sensors with our ground truths. So we showed our kinematic algorithm with invariant sensor placement assumption is not that helpful to do motion estimation. So it preclude reliable post-estimation, post-reconstruction. And then finally, we explored some basic machine learning techniques for full body motion tracking. So in two approaches. The best approach is direct joint angle estimate, the end-to-end. It is accurate on the data set, but it has limited generalizability. So it may be good for activity recognition. So another approach we tried is the learning RSB, estimated sensor displacement using deep neural networks. So it is more generalizable, but it has limited accuracy since we feed into the ground truth with very noisy data.
So how do you conclude about generalizability? Do you have done experiments on unseen and seen?
Yes. So basically, other than the data set, we tried collect the data. We tried to do experiment on unseen object with unseen motions. So the result shows if we are using the end-to-end estimation on unseen motions, and the recovery rate is precision is not good. Because the DNN never seen the particular kind of motion. Like we can do random motions, not the 5 motions we have in the data set. So it's not good. So it's not generalizable. But if we use the first approach, the sensor displacement learning approach, it is more generalizable. It performs slightly better than the first approach. Means we try to quantify the sensor displacement, and then we still use the kinematics to solve the equation. So there's no problem with generalizability since we are using the kinematics to solve the particular problem. So Last one, I'm going to talk about future work because I think the project has a very strong potential behind it. So what we can push in the future. So first of all, hardware improvement. So as you can see, it's a prototype as we built from my internship. So we can improve the hardware with flex PCBs with like less wiring in the system and more robust. And we can also pursue out-of-studio data collection. So now all the data are collected in the studio because we need the Kinects to collect ground truths for us. But we can pursue out-of-studio data collection, meaning we need non-optical trackers for our ground truths. We can create a larger data set with richer everyday motions. If we can do out-of-studio data collection, it would be very easy to do this. We can just ask the subject to wear the system whole day, and we collect the data. So the ground truth could be the initial, as you see in my second video, with straps. We can strap them inside and then put the garment on top of it. So as we can see in the machine learning approach, it's very preliminary. We can explore improved neural network architecture, as RNN, LSTM, or other better architectures. So on top of this, we can try to do a fusion technique. Like we can build an ensemble of all different trackers and try to arbitrate between them. Sometimes the kinematics performs well, sometimes learning RSB performs well, sometimes the end-to-end or other networks may perform well. We can arbitrate between them and fuse and get to the final estimation. So other than that, we can do calibration-free motion capture. Because for all the motion capture system out there, we need to calibrate. But our advantage of the system is we use the densely covered body sensor network. We have the sensor redundancy. We can try to solve the calibration problem by using sensor redundancy. Also, we have different modalities. We have infrared. We also have ultrasonic sensors on the body, but we didn't use it for this particular project. So we can do land-based resetting, which means when your arm cross here, the ultrasonic will know this is the minimum value of the ultrasonic, and then my arm is 90 degrees. That's landmass-based resetting. And with a better pose tracker, we can do more human environment interaction, such as we can do odometry on IMU. We all know using IMU to do odometry is not reliable because of the internal drift and the sensor noise. But we may be able to compensate the noise using multiple sensors and also using different sensor modalities. We can also do graphical SLAM. Say if the person is interacting in a room, how, like in a hallway or in a map, how could we build the map, like a graphical map of it based on my odometry? And also multimodal SLAM is more like if we can include ultrasonic sensor to do like one layer mapping of the occupancy grid. It's also portable if we have a good pose tracker. So the final point I want to mention here is the project has a huge potential for healthcare, for other new applications. We can include this thing into the cloud. We can integrate the motion capture of the body sensor network with our mobile devices, like our smartphones, and stream the data to the cloud. And for future reference, for like medical analysis and for other new applications. Okay, I think that concludes my talk, and I'm open for questions now.
DNN, the end-to-end solution that DNN. So the input is a window of time.
Yes.
So on one of the first video, you see that the DNN tried to predict the motion that is happening. Can you go back in one of them?
Yeah, you're right.
So it's actually anticipating the actual motion. So that is an overfitting of the motion, right?
The first video?
Yes. So
The first motion is upper arm movement. Starting from the T-pose, the subjects need to use the shoulder joints to move the upper arm and reach 4 extreme positions. Since both the baseline and DNN tracker assume zero translation and rotation of the hip, we manually fix the hip of the ground truth tracker.
So basically, you're right that we did observe that there is preemption by a few frames. It's probably because the frames are not very synchronized. So he did the synchronization manually.
That's maybe the video synchronization.
So he
problem.
took this first video, we took the second video, third video,
Oh, okay, so it's
synchronized it
continuous.
manually.
Okay. I see.
So each frame was synchronized.
But this one
individually.
is the validation data set.
This is
That's the
data
test set, yeah.
Okay, that's it. Okay.
Yes.
So we shouldn't take that too seriously. Because basically what we do is we have like 2,500 frames and we look at the first frame where there is a first movement and then use that as the starting point to synchronize them. The two videos.
On the video.
On both the videos. So they're all different videos.
4 different videos, yeah.
So, yeah, one of the things of the hardware that you said is you have a way of calibrating and synchronizing all 38 sensors. How accurate is that? I've never seen anyone use so many IMUs. So, in general, like for sensor fusion, I've seen people use cameras and IMUs. I've seen 2, 3 IMUs.
Yeah, not so
It's
many.
already very hard to precisely calibrate them. So here it seems that it will be kind of crucial if you want to aim for accuracy.
Yeah.
Can you comment a little bit?
Yes, so basically, I know the most number of IMUs people use for motion tracking is 8. There's a data set out there with 8 IMUs, but we have 38. Yes, that's a lot. So for the calibration, so we perform a T-pose. So for this, we assume all the joint angles to be 0, 0, 0. And then we ask the subject to hold the T-pose for like 15 seconds. So we try to recover the orientation of because it's stable. So we are trying to recover the relative orientation from the IMU to the body part. So we can do that all at the same time.
So it's an auto-calibration system.
It's auto, yeah, it's automatic.
It's not pre-calibration.
It's not. You need to take one and calibrate it. Take one. No, you can do it all by itself at one time.
Yeah.
That's the calibration
Also, like for the same person, if they take the jacket off and wear it again, I think it has to be recalibrated.
Yes,
Right.
of course.
Okay,
It's
that's
even the thing is, even if the person moves a little bit, the ideal case you need to recalibrate it because the sensor moves. But that's a problem we are tackling, because we don't have the luxury to calibrate every single time. That's a problem. Yes.
So one of our goals is to get rid of this calibration.
Yeah.
In the end. So the second question is synchronization. Can you comment on that?
Um,
One of the comments I can make is each individual sensor is not transmitting separately.
Okay.
So all of these sensors are connected to one CPU through a wire.
Yeah.
Oh,
So then the data is
I missed
aggregated.
that. I missed that.
Exactly. So that's running at 80 megahertz.
I see.
And so that's running pretty fast. So the time difference, delays between.
I missed that part,
Yeah.
so that's why I was in my.
So ideally we would want to go to individual transmitters on individual.
Right.
That's a difficult problem. That's another difficult problem we need to solve.
So I wanted to point out one paper from 2017, which is very relevant. I mean, I was actually very impressed. They're basically trying to solve the same problem. They have 6 IMUs, and they're like people like running and riding a bicycle, jumping over a fence. They're basically able to do unconstrained motion capture, completely like geometrically solving.
Yeah, it does. You can solve it also. So it will work pretty well as long as it's trapped.
Right.
It works pretty well.
So is your sorry.
But I was gonna this kinematic constraint of the skeleton seems crucial, right? And currently it's not being used here because you're modeling only rotations, right? You don't actually model full kinematics.
Yeah.
We don't track position. We don't track velocity. It's only rotations. Yes.
It seems
Because that's only-
necessary for accuracy.
So for IMUs, I don't think it's reliable to use IMUs to track position, because you cannot just easily integrate them.
But using the constraint of the limb length, basically there's a rigidity constraint.
But if you want to integrate the constraint for that, that means you need position tracking. We are not doing this. Basically, if I put the IMU on my lower arm, I put another on my upper arm, I can just track this angle. We don't need to include the kinematic, the length information of the limb.
So what he says is to get displacement. So when you want to say that your hand cannot move here or versus here, right? You need to understand how far has the sensor moved in space. So that's distance.
Yeah.
Okay. Like you see, when I move my hand here, the sensor has moved from here to here. So I need to be able to measure this distance, and that's difficult to do with IMUs.
This
Okay.
paper, so this paper might be interesting for you.
Yeah,
because
maybe
they
they
somehow
do.
they're able to do that. I think they're using extra information about the human body shape.
Yeah.
You can add hard constraints like the angle cannot be more than this much. You can saturate it, but trying to do it, it's doable. But even more harder with the moving sensors. That's the major challenge we're trying to solve here.
So the real challenge here is that clothes is loose. The IMUs are not attached
Yeah.
tightly to the body, right?
Yeah.
Yes.
That's
That's the real
we believe
challenge.
that breaks a major barrier for this technology.
because you can mount it.
Because as you're sitting now, I can track your body position on your smartphone. We can mount it on your garments. And
Right.
We can track
But
your body.
otherwise, I could have a tight suit. But
Yeah,
that
not comfortable to
the
sit here.
difference is between tight suit and the normal clothes.
Yes.
Yeah. Because for tight suit, they are like ready technology and
Yes.
yeah.
So that's the main difference.
And for the end-to-end model, deep learning model, so like your classes are basically the actions that you're performing.
No, it's all the joint angle values. It's not classes. It's doing regression. So I'm trying to predict the whole body's angles. So
Okay.
yeah, the input is the IMU data. The output is all the angles throughout the body. 12 angles. If you say all the angles, that's 36.
Then like how is it not generalized if you're just predicting angles?
Oh, so because in the data set we have only 5 motions: upper arm, lower arm, working, boxing, and arm swing. So if we are doing motions other than that, it may not be working well. That's not generalizable.
But like even in that motion, so let's say even if you're boxing like this, like mostly like all of the angles are covered, right?
Yes, yes.
So like
So-
if you perform any other action also, but if the angles are kind of similar,
Yeah, so
that
a
would
larger
be,
data set will definitely
Yeah,
help.
If you have a very big data set,
Very big data
covers
set.
every motion.
And that gives a large number of possibilities in 3D
Yeah.
space for you, every angle, right? If we can cover that, it might work.
in the other procedure where you said you'll estimate theta and then do kinematics to get angles. So like what's different in that? Like how is that more generalized?
So that is, we are trying to predict the sensor movement on the body part. So this is a much smaller space than all the body movement. So
Okay,
the
so you
sa-
mean like you need much less data set
Data.
for that?
Yes, hopefully we just need a limited amount of data set and we can try to predict unseen motions just by predicting this. Yeah.
Let's thank, if you don't have more questions, let's thank the speaker again.